Stan Gibilisco here with the next episode in the continuing saga of the complex number primer. At the end of the last episode, I indicated that I was going to tell you what a vector is, because a lot of people don't seem to understand the concept for whatever reason. First, let's look at the concept of a simple number, such as a real number on a real number line, like that. We can express any real number as a point along this line, thereby indicating its value. However, we get into some trouble when we want to go positive or negative. If we simply indicate the magnitude or the extent that a number has, say 1.35, that would appear as a point right about there. If we indicate minus 1.35, it'll turn out to be right about there. Well, so far so good. But we have a problem. If we want to indicate both positive and negative real numbers as simple magnitudes, that is, quantities that we would encounter in everyday life, such as the weight of a person, or say the speed of the wind, or the speed with which you're driving down the highway. Suppose that we wanted to express it as barometric pressure in millibars or inches of mercury or something like that. We get into trouble because when we want to express a simple displacement or distance, there's a difference. Displacement suggests direction, but distance simply suggests extent. Both 1.35 and minus 1.35 are the same distance from zero on this line. And if we want to use some other point, if we want to try to obtain an absolute standard for distance, we can't do it anywhere on this line without having an ambiguity occur somewhere, like we would get here. Well, we could suggest minus 100 as the reference point, but then we'd encounter the same problem with any 2 points that were that far away from minus 100 on the line. So a quantity like 1.35 is a scalar. It's called a scalar because it indicates scale or extent. However, if we want to seriously start talking about positive and negative and differentiate them, we might say that positive numbers go to the right negative numbers go to the left of zero. But once we get into expressing direction in addition to extent, a simple scalar or expression of extent does not do the job anymore for us. We have to specify a direction as well. In the case of a number line like this, it's pretty straightforward. We only have two possible directions, but infinitely many possible extents. But now, let's suppose that we want to express a point on a coordinate system, let's just take the simple compass. North, east, south, west. Sometimes people will express the direction going around clockwise from north in degrees. This particular direction here would be about 90, 180 plus 45, roughly 225 degrees. That's the direction. And we might, that is southwest, as you can plainly see. Now suppose that we are driving on a highway at 50 miles an hour. 50 miles an hour is about a little less than that, about 80 kilometers per hour for those of you who want to do metric. 50 miles an hour. If we're driving southwest and we're going 50 miles an hour, that's one thing. If we turn onto another road and we find that the speed limit there is 50 miles an hour and we want to go on that road, but it runs off in some direction like this, maybe that's 330 degrees. 50 miles an hour again. Miles is abbreviated MI, per is a slash, and hours H, miles an hour. Sometimes you'll see it written like that. Anyway, the speed-wise, 50 miles an hour is the same magnitude or extent of the quantity, but the direction is clearly different, and so we have a vastly different situation. We're going to end up in a vastly different place if we drive for a few hours at 50 miles an hour going north-northwest than we will get if we drive for a few hours going 50 miles an hour going southwest. So the direction is different. A vector takes into account both magnitude and direction. So these representations on the coordinate system like this are vectors. Scalars, 50 miles an hour, they're the same. Directions are different. That's all a vector is. I might conclude this little episode with a real-life experience. I was in the eye of Hurricane Andrew in 1992, right exactly in the center of the storm. Counterclockwise circulation like this. The eye was about 18 miles in diameter. The storm was moving from east to west, almost directly from east to west at roughly 18 miles an hour. These are approximate figures, I don't remember exactly, but that's pretty close. The eye wall of the storm was a very concentrated ring of thunder showers right around the eye, like that. This was where the extreme winds were. I was located in a town called Homestead. They may have capitalized the name of their town before Hurricane Andrew, but they probably didn't feel much like capitalizing it after Hurricane Andrew, because Andrew pretty much took Homestead, Florida off the map. The people were still there, but the infrastructure was destroyed. Anyway, the vector of the hurricane's motion, we might say, was 18 miles an hour. going from from east to west, that would be in a direction of 270 degrees by the compass. That would be the vector of the hurricane's motion. During the first half of the hurricane, as it moved over me, the wind blew out of the north at a sustained speed of something on the order of 120 miles an hour. The gusts were probably more like 160 or 170, but the sustained wind out of the north at 120 miles an hour, so we'd call that vector, since it's going towards the south, we would call that vector 120 miles an hour, 180 degrees. That would be the wind vector. Then the eye passed over. These extreme winds lasted for 45 minutes. I remember this because I made a point of it to burn it into my memory. Not that you have to try very hard when you're having 120 mile an hour sustained wind. That tends to burn itself into your memory pretty well. Anyway, this hurricane went past. Then the second half of the hurricane came through. The wind blew pretty much from south to north, so a compass direction of 0 degrees. Because the storm had moved over land, its intensity was diminished quite a bit. I don't know what the sustained winds would have been in the second half of the hurricane, but I imagine they were probably something on the order of 100 miles an hour. A mere breeze compared to 120. The destructive power of 120 mile an hour wind is quite a lot more than 100 miles an hour. It's a lot more than the difference would suggest. Anyway, that would be the vector of the wind during the second half of the storm. Now, we're pretty much familiar with what a vector is. It is a quantity with two components, magnitude and direction. So, we're ready now to use vectors to describe complex numbers, real axis, imaginary axis. We are now ready to describe complex numbers in the complex number coordinate system as vectors, and that I will do in the next episode of this ongoing adventure. Stan Gibilisco signing off.